Today we are going to talk about reflection and transmission of transverse waves of the string connected to another string with different mass density. The wave will be assumed to be propagated from negative infinity, and the boundary condition between two waves will be x equals 0. Also, the string with different mass density will also be assumed to be from x equals 0 to positive infinity. Before jumping into the discussion directly, the concepts of mass density, impedance, and boundary conditions will be introduced first. Let's consider an oscillating string and think about the driving force acting on it. Looking at a small segment of string as displayed on the left-hand side of the page. By equating the net force obtained from Newton's second law, which is mass times acceleration, and from the net vertical tension force, we get F equals mu delta x, the second differential of the psi with respect to time, equals t d psi dx at x plus delta x minus t d psi dx at x. Mu is the mass density, which is mass per unit length, and t is the tension on string, and psi is the vertical displacement of the segment. After rearranging this equation above, we get the second differential of psi with respect to time equals t over mu times d psi dx at x plus delta x minus d psi dx at x over delta x. Then from the formal definition of derivative, we reached the wave equation with the wave velocity written as c equals square root of t over mu. Therefore, the wave number k and angular frequency has a dispersion relation of square root of t over mu equals the frequency over k. Now moving on to the definition of impedance. Impedance, the unit for waves, is a measure of resistance that a wave encounters, and it depends on the mass density mu. For a stretched string, it is given by Z0 equals square root of t times mu, where t is the tension and mu is the mass density. Note that the higher impedance leads to more resistance to the wave motion. Impedance can also be defined from simple harmonic oscillation theory, which is Z0 equals the driving force over velocity, which can be simply written as t over c, and the driving force is therefore Fd equals Z0 d psi dt at x equals 0. Thus, we can calculate the impedance from t over c and the square root of t times mu. Now we can move on to introduce the boundary conditions acting on waves.
Now let's look at the boundary condition at x equals 0. The superposition wave of initial and reflected waves amplitude is the same as transmitted waves as two strings are tied to each other. This is shown as the equation 1. The drag force by the second wave is balanced by the transverse force from the first string at the boundary, which is x equals 0. Note that we have got the transverse force by resolving tension in y direction with small angle of approximation. With impedance being force divided by speed and D'Alembert relationship, we get the relationship of third equation by substituting first equation into the second equation.
Now we're going to be looking at the animation of waves for different scenarios. For the first scenario, we have a free end. This is where the boundary condition mass density is equal to 0. So as you can see from the incident and reflected waves, they both have the same amplitude. So when the two peaks align, we have constructive interference, but the resultant amplitude is double the amplitude of the incident wave. Now, when the peak and the trough of the incident and reflected wave coincide, we have destructive interference. This is where the resultant amplitude is equal to 0. As you can see from the superposed wave varying from double the amplitude to 0. And the next animation shows a string with a smaller mass density. As we can see from the animation, the reflective wave has a smaller amplitude compared to the initial incident wave. And moving on to the next animation, which is showing where the second string has a larger mass density compared to the first one. As you can see, the reflective wave has a very small amplitude compared to the initial. Moving on to the next animation, where the two strings have the same mass density. As you can see from the animation, the initial wave is just transmitted through, and the reflective wave has zero amplitude. And the final animation shows a scenario where the strings have fixed ends. From looking at all the animations, we can conclude that the mass density affects the motion for both new string and the original string which the wave has been propagating from. For smaller density, the wavelength increases. For larger density, the wavelength decreases.